The cylindrical and spherical polar coordinate systems are special cases of the curvilinear coordinate system. For many types of motion it is more convenient to use curvilinear coordinates when we describe the position of a point in space, since these coordinates are more suitable for the geometrical arrangement of the given case, that is, they can be adapted to the symmetries of the problem. Let us denote the curvilinear coordinates of an arbitrary point P in the space with the triplet U1, U2 and U3. The most convenient method to define these coordinates when they are given as functions of the Cartesian coordinates. For the point P described with the rectilinear coordinates, we can specify the coordinate transformations for the curvilinear coordinates U1, U2, and U3 as functions of x, y and z. We also have the inverse coordinate transformations for the Cartesian coordinates as functions of the curvilinear ones. That is, we have two equivalent descriptions of the position of P in the coordinate space. We can draw the coordinate lines through the point P, for which one of the curvilinear coordinates is running over its domain, while the other two coordinates have fixed values, given in the point P. As opposed to the Cartesian coordinates, these coordinate lines are not necessarily straight lines and not even mutually orthogonal to each other in the point P. The Cartesian coordinates are regular in the sense that the coordinate lines are the x, y and z axes, which are perpendicular to each other. We can also consider the point sets, where one of the coordinates is fixed while the other two coordinates are arbitrary. These two-dimensional point sets are called coordinate surfaces. In the case of the Cartesian coordinates, for x is equal to a constant we have a family of planes parallel with the yz plane. Here we see the plane for x equal to 0 in one of the octants of the coordinate system. For the points defined by y equal to a constant, we have planes parallel with the xz plane. Here we also see the plane for y equal to 0 in one of the octants of the coordinate system. The points for z equal to a constant represents the planes parallel with the xy plane. Here we see the plane for z equal to 0 in one of the octants of the coordinate system. The coordinate surfaces of the curvilinear coordinates are generally not planes. For the points defined by u1 equal to a constant, we have surfaces on which the coordinate lines u2 and u3 run. For the points defined by u2 equal to a constant, the coordinate surface contains the coordinate lines u1 and u3. The coordinate surface for points defined by u3 equal to constant has the coordinate lines u1 and u2. It follows from these definitions that the coordinate lines are the intersections of the coordinate surfaces. In the case of the Cartesian coordinates they coincide with the x, y and z axes. In the case of the curvilinear coordinates, we can only say that the coordinate lines are the intersections of the coordinate surfaces. The Cartesian basis vectors ex, ey, and ez point from the origin into the direction of the axes. They are mutually orthogonal and can be considered as the normal vectors of the yz, xz and the xy planes respectively. The curvilinear coordinate basis vectors e1, e2 and e3 are not necessarily orthogonal to each other, but they are the normal vectors of the coordinate surfaces in the point P. If we want to describe the motion in a curvilinear coordinate system, we need to determine the explicit forms of the basis vectors of the coordinate system. We can use the coordinate transformations between the Cartesian and the curvilinear coordinates to obtain these expressions. The basis vectors of the Cartesian coordinate system are already given. Their directions are determined by the axes of the coordinate system and they have unit length. Now we consider a curvilinear coordinate system with the coordinates u1, u2, and u3, and determine the explicit forms of its basis vectors e1, e2, and e3. In this calculation, we will use the functions of inverse coordinate transformations, which map the curvilinear coordinates to the Cartesian ones. The natural basis vectors of the curvilinear coordinates can be written as the linear combinations of the Cartesian basis vectors, where the coefficients are the partial derivatives of the Cartesian coordinates with respect to the curvilinear ones. That is, the natural basis vector gi for the coordinate ui with the index I running from 1 to 3 is given by the partial derivative of x with respect to ui times ex, plus the partial derivative of y with respect to ui times ey, plus the partial derivative of z with respect to ui times ez. We can conclude that the components of the natural basis vectors in the Cartesian coordinate system are the partial derivatives of the Cartesian coordinates with respect to the corresponding curvilinear coordinates. It can be shown that the vectors are linearly independent from each other, therefore they form a basis. The length of each basis vector is given by the square root of the squared sum of its components, which is not necessarily unity. Now, the coordinate basis vectors of the curvilinear coordinates are defined by the normalized natural basis vectors. That is, EI is equal to GI divided by the length of GI, where the index I is running from 1 to 3. Here we can see the explicit forms of the coordinate basis vectors, which are complicated expressions. However, we can use the Jacobian J of the coordinate transformations between the Cartesian coordinates and the curvilinear ones to compute the basis vectors. In fact, the columns of the Jacobian will help us to determine them. Since each column of the matrix J contains the nominator of the fraction defining the corresponding basis vector, it is enough to read out their components from the column vectors of the matrix, denoted with J1, J2 and J3. The only missing factor is the normalization, which can be computed from the squared sum of the column vectors. Then each column vector is equal to the corresponding basis vector times the length of that column vector. We apply this simple method to determine the basis vectors of the cylindrical and spherical polar coordinates. Let us start with the computation of the basis vectors for the cylindrical coordinates. Here the curvilinear coordinates u1, u2, and u3 are the quantities ρ, phi and z, which are defined in this figure. We also have the explicit forms of the Cartesian coordinates as the functions of the cylindrical ones. By using these functions, we would like to determine the basis vector e ρ, which is the unit tangent of the ρ line translated to the point P. The basis vector e phi, which is the unit tangent of the phi line translated to the point P. And the basis vector e z, which is the unit tangent of the z line translated to the point P. We know that the position vector pointing at P has the basis expansion ρ times e ρ, plus c times ez. By taking the derivatives of the coordinate transformation with respect to ρ, phi, and z, we can compute the Jacobian of the transformation. Now we can determine the basis vectors from the column vectors of the Jacobian. E ρ is given by its first column vector. Since the length of this vector is the square of sine phi plus the square of the cosine phi, which is 1, the components of E ρ are the same as the column vector. Its x component is cosine phi and its y component is sine phi. Similarly, the second column vector gives the basis vector e phi. Since the length of the second column vector is ρ, we need to divide this vector with this length to obtain the basis vector. Then the x component of the basis vector e phi is minus sine phi, and its y component is cosine phi. The third column with its unit length shows that the third basis vector is simply ez. We can follow the same procedure for the spherical polar coordinates. Here the curvilinear coordinates u1, u2, and u3 are r, theta, and phi, with the definitions in this figure. The coordinate transformations are somewhat more complicated than in the case of the cylindrical coordinates. The basis vector er is the unit tangent of the r line at the point P. The basis vector e theta is the unit tangent of the theta line at the point P. And the basis vector e phi is the unit vector of the phi line at the point P. The form of the position vector is simply r times er. The derivatives of the Cartesian coordinates with respect to the spherical polar ones give the Jacobian of the coordinate transformation. Then we can determine the basis vectors from the columns of the matrix again. The first column of the matrix gives the basis vector er. Since the length of the first column is equal to 1, the components of the column vector are equal to those of the basis vector er. The x component of the basis vector is sine theta times cosine phi. Its y component is sine theta times sine phi. And its c component is cosine theta. The second column vector of the Jacobian determines the basis vector e theta, where the length of the column vector is r. If they divide its components by r, we obtain the components of the basis vector e theta. Then its x component is cosine theta times cosine phi. Its y component is cosine theta times sine phi. And its c component is minus sine theta. The last column vector of the Jacobian determines the basis vector e phi. The length of this column vector is equal to r times sine theta, and the column vector divided by this length will be the basis vector. Then its x component is equal to minus sine phi, and its y component is cosine phi. Now we obtain the full set of the coordinate basis vectors, both the cylindrical and spherical coordinate systems. If we want to describe the velocity and the acceleration of a moving body in the terms of cylindrical coordinates, we need to express the parametric derivatives of the basis vectors as their linear combinations. In the cylindrical coordinate system, the coordinates ρ, phi, and z become the functions of the time parameter t. Therefore, we have to differentiate these functions in the basis vectors e ρ and e phi with respect to t to obtain the derivatives of these basis functions. Since the basis vector ez does not depend on the parameter t, its derivative with respect to it will vanish, which means it is a constant vector. Let us start with the computation of the first-order derivatives of the basis vectors. If we differentiate the basis vector e rho with respect to t, then the x component of the derivative vector will be minus phi dot times sine phi, and its y component will be phi dot times cosine phi. Now we can factor out the derivative of phi, and the rest of the terms gives nothing but the basis vector e phi. Then the parametric derivative of the basis vector e rho is equal to the basis vector e phi multiplied by the parametric derivative of the azimuthal angle phi. Similarly, the x component of the derivative of the basis vector e phi is minus phi dot times cosine phi, and its y component is minus phi dot times sine phi. After factoring out the derivative of the azimuthal angle, the rest of the terms gives minus 1 times the basis vector e rho. Then the parametric derivative of the basis vector e phi is equal to the basis vector e rho multiplied by minus the parametric derivative of the azimuthal angle phi. This is an important result, which shows that the parametric derivatives of the basis vectors can be expressed in the terms of the basis vectors themselves. The second-order derivative of the basis vectors can be calculated by differentiating their first-order derivatives. Then the second-order derivative of the basis vector e rho is equal to phi double dot times e phi, plus phi dot times e phi dot. Since e phi dot is equal to minus phi dot times the basis vector e rho, the second term in the right-hand side can be written as minus phi dot squared times the basis vector e rho. The second-order derivative of the basis vector e phi is equal to minus phi double dot times e rho, minus phi dot times e rho dot. Here we can also replace the derivative of the basis vector e rho in the second term with phi dot times e phi. Then the second term can be written as minus phi dot squared times the basis vector e phi. As a result, we could also express the second-order parametric derivatives of the basis vectors as the linear combinations of the basis vectors themselves. In fact, the second-order derivatives are not necessarily needed to describe the acceleration in cylindrical coordinates, but we present their derivations here for the sake of completeness. Before differentiating the velocity vector written in cylindrical coordinates, we can replace the first-order derivatives of the basis vectors with the expressions in the first purple box. Then the differentiation of the velocity leads to equations containing the first-order derivatives of the basis vectors, which can be replaced with the same expressions again. We can provide some geometric interpretations for the derivatives of the basis vectors of the cylindrical coordinate system, which can be demonstrated in the figure. Here we can see the point P described with the coordinates ρ, phi and z. At the point P, we can draw the basis vectors e rho, e phi and e z. If we translate the point P into the point P' along the curve phi equal to constant, the point P' can be described with the coordinates ρ', phi and z'. Since the azimuthal angle phi is constant, its derivative vanishes. Therefore, the derivatives of the basis vector e rho and e phi also vanish. That is, the basis vectors do not change along the phi line. As a result, the basis vectors in the point P' are the same as the original ones in the point P. If we translate the point P to the point P double prime along with the circle of constant ρ in the z-plane, the coordinates of the point P double prime will be ρ, phi double prime and z. Since we change the azimuthal angle, its derivative does not vanish. Neither do the derivatives of the basis vectors. As a result, the basis vectors are changing as we move the point P along the constant ρ circle. For the basis vectors erected in the point P double prime, both the vectors e rho and e phi point into different directions compared to those in the point P. We also saw that the derivatives of the basis vectors are proportional to the derivative of the azimuthal angle, and the derivative vectors point into the directions of the basis vectors. This statement can be demonstrated in this figure with the z-plane lying in the plane of the figure. Here we see the constant ρ circle is passing through the point P given by the position vector r. The basis vector e rho at the point P has the same direction as the position vector. If we rotate the position vector with the angle delta phi, we move the point P into the point P'. Then the basis vector at P' points into a new direction. We can translate this basis vector to the point P, and construct the difference between the translated basis vector and the original one, labeled with e rho dot. We can see that the difference vector is indeed the derivative of the basis vector if we translate it along the arc between the points P and P'. If the point P' approaches the point P, then the angle delta phi becomes infinitesimally small. As a result, the difference vector becomes perpendicular to the position vector, that is, it becomes a tangent to the circle. And its length will be equal to the change delta phi in the azimuthal angle. Then the derivative of the basis vector E rho is a tangent to the constant rho circle, that is, it has the same direction as E phi do, and it is proportional to the derivative of the azimuthal angle. We can use the same procedure in the case of the derivative of the basis vector E phi. Here the basis vector E phi is depicted at the point P, which is the tangent to the circle at P. If we rotate the position vector with the angle delta phi again and move the point P into the point P', then we can draw the basis vector E phi at P', which will be the tangent to the circle at that point. Let us transport this vector to the point P. We can see that the angle between the transported basis vector and the original one is equal to delta phi. We take the difference of the transported basis vector and the original one, which is labeled by E phi dot. This difference vector can be transported to the circle between the points P and P', and we can take the limit as angle delta phi approaches 0. In this limit the difference vector will point in the same direction as the position vector do. Therefore, it will be parallel with the basis vector E rho, but it points to the opposite direction. Since the angle between the transported basis vector and the original one is equal to delta phi and this angle is infinitesimal, the length of the difference vector is the change in the angle again. Then we see that the derivative of the basis vector E phi is perpendicular to the tangent to circle in the point P, that is, it has the opposite direction to E rho, and it is proportional to the derivative of the azimuthal angle. We can differentiate the basis vectors of the spherical polar coordinate system in the same way. The coordinates r, theta, and phi are the functions of the parameter t now. If we consider the expressions of the basis vectors, we can see that these vectors depend only on the angles theta and phi. Therefore the derivatives of the basis vectors will contain the derivatives of the angles. Let us compute the first-order derivatives of the basis vectors. In order to obtain the derivative of the basis vector ER, first we apply the Leibniz rule and the chain rule for its x component, which is the product of sine theta and cosine phi. As a result, the x component of the derivative of the basis vector is equal to theta dot times cosine phi, minus sine theta times phi dot times sine phi. We can apply the same rules to the differentiation of the y component of the basis vector ER. Since the y component is given by sine theta times sine phi, its derivative is equal to theta dot times cosine theta times sine phi, plus sine theta times phi dot times cosine phi. Similarly, since the z component of the basis vector ER is cosine theta, its derivative is equal to minus theta dot times sine theta. Now we can factor out the expression phi dot times sine theta from the second and the fourth terms in the right-hand side. This gives phi dot times sine theta, times the sum of minus sine phi times ex and cosine phi times ey. We can also factor out the derivative of theta from the rest of the right-hand side, which gives theta dot times cosine phi times ex plus cosine theta times sine phi times ey minus sine theta times ez. Now we recognize that the expressions in the parenthesis in the first term give the basis vector E phi, whereas the expressions in the parenthesis in the second term give the basis vector E theta. Then the derivative of the basis vector ER can be written as phi dot times sine theta times E phi, plus theta dot times E theta. We can follow the same procedure when we compute the derivative of the basis vector E theta. The x component of E theta is cosine theta times cosine phi, and its derivative can be written as minus theta dot times sine theta times cosine phi, minus cosine theta times phi dot times sine phi. The y component of the basis vector E theta is cosine theta times sine phi, and we can write its derivative as minus theta dot times sine theta times sine phi, plus cosine theta times phi dot times cosine phi. The z component of E theta is simply minus sine theta with the derivative of theta dot times cosine theta. If we factor out minus theta dot from the first, the third, and the last terms, we obtain minus theta dot times sine theta times cosine phi times ex plus sine theta times sine phi times ey plus cosine theta times ez. We can also factor out the term phi dot times cosine theta from the second and the fourth terms, which gives plus phi dot cosine theta times the sum of minus sine phi times ex and cosine phi ey. Now we see that the terms in the parenthesis of the first term give the basis vector er, whereas the terms in parenthesis of the second term are equal to the basis vector E phi. Then the derivative of the basis vector E theta is equal to theta dot times the basis vector ER, plus phi dot times cosine theta times the basis vector E phi. If we want to compute the derivative of the basis vector E phi, we take another route. The x component of e phi is simply minus sine phi with the derivative minus phi dot times cosine phi. Its y component is cosine phi with the derivative minus phi dot times sine phi. Now we can multiply both the x and the y components of the derivative by the sum of squares of sine theta and cosine theta, which is identically 1. Then we can factor out the expression minus phi dot times sine theta, which gives minus phi dot times sine theta times the sum of sine theta times cosine phi times ex and sine theta times sine phi times ey. If we factor out the expression minus phi dot times cosine theta, we obtain minus phi dot times cosine theta times the sum of cosine theta times cosine phi times ex and cosine theta times sine phi times ey. Finally, we can also subtract the expression phi dot times sine theta times cosine theta from the derivative and the same time add to it. Then the first and the third terms in the right-hand side give minus phi dot times sine theta times er, and the second and the last terms give minus phi dot times cosine theta times e theta. Now we see that we could express the derivatives of the basis vectors in the terms of the basis vectors themselves. The derivative of the basis vector er is the linear combination of the basis vectors e theta and e phi, where the coefficients of the vectors are functions of the angular coordinates and their derivatives. The derivative of the basis vector e theta can be written as the linear combination of the basis vectors er and e phi with the coefficients depending the angles and their derivatives. The derivative of the basis vector e phi is also a linear combination of the other two basis vectors, er and e theta, where the coefficients still depends on the angles and their derivatives. By applying these expressions computed for both the cylindrical and spherical polar coordinates, we can give the first and the second order derivatives of the position vector in these coordinate systems. As we have already seen, the equations of motion of a point-like body in kinematics are the position vector of the body, and its in first and second order derivatives, expressed as vector-valued functions of time. Now let us find out how the equations of motion can be written as component equations in the three coordinate systems presented here. The position vector and its derivatives have the simplest expressions in Cartesian coordinates, since the basis vectors of the Cartesian coordinate system do not depend on time. The position vector r has the x, y and z coordinates in the direction of the x, y and z axes. The coordinate components of its time derivative are simple the derivatives of the x, y and z coordinates. Similarly, the coordinate components of its second order derivative are simple the second order derivatives of the x, y and z coordinates. In the cylindrical coordinate system, these expressions will be more complicated since two of the basis vectors are also changing in time. The position vector r has two coordinate components, ρ in the direction of the ρ coordinate line, and z in the direction of the z-axis. Since the basis vector e ρ depends on the time parameter t, the derivative of the position vector is equal to ρ dot times e ρ, plus ρ times e ρ dot, plus c dot times ez. We have already seen that the derivative of the basis vector e ρ is equal to phi dot times e phi. Then we obtain the first order derivative of the position vector. Its ρ component is the derivative of the ρ. Its phi component is ρ times the derivative of phi. And its c component is the derivative of z. Now we differentiate the first order derivative of the position vector r. The derivative of the first term of r dot, that is of the expression ρ dot times e ρ, is equal to ρ double dot times e ρ, plus ρ dot times e ρ dot. The derivative of the second term of r dot, that is of the expression ρ times phi dot times e phi, is equal to ρ dot times phi dot times e phi, plus ρ times phi double dot times e phi, plus ρ times phi dot times e phi dot. The derivative of the third term of r dot, that is z dot times ez, is simply z double dot times ez since ez is constant. We see that the second order derivative of r contains the derivatives of the basis vectors e ρ and e phi, which we already computed. Therefore we can substitute them into this expression. Then we obtain the components of the second order derivative of the position vector. Its ρ component is ρ double dot minus ρ times phi dot squared. Its phi component is ρ times phi double dot minus 2 times ρ dot times phi dot. And its c component is simply z double dot. We can follow the same procedure in the case of the spherical polar coordinate system. In spherical coordinates the expression of the position vector r is very simple, it is r times er. Then the derivative of the position vector is given by r dot times er, plus r times er dot. Here we already know the derivative of the basis vector er, which we can substitute into the derivative of position vector r. Then the derivative of the position vector r is the following. Its r component is simply r dot. Its theta component is r times theta dot times sine phi. And its phi component is r times phi dot. Now we differentiate the derivative of the position vector r. The derivative of the first term in r dot, that is of the expression r dot times er, is given by r double dot times er plus r dot times er dot. The derivative of the second term in r dot, that is of the expression r times theta dot times sine phi times e theta consists of four terms. R dot times theta dot times sine phi times e theta. Plus r times theta double dot times sine phi times e theta. Plus r times theta dot times phi dot times cosine phi times e theta. Plus r times theta dot times sine phi times e theta dot. The derivative of the third term in r dot, that is of the expression r dot times phi dot times e phi, is equal to r dot times phi dot times e phi. Plus r times phi double dot times e phi. Plus r times phi dot times e phi dot. Besides the expression of the derivative of the basis vector er, we also computed the derivatives of the basis vectors e theta and e phi, as we can see in the left-hand side of this box. We can eliminate the derivatives of the basis vectors by substituting these expressions into the second-order derivative of the position vector r. Then the r component of the second-order derivative is equal to r double dot, minus r times theta dot squared times the square of sine phi, minus r times phi dot squared. Its theta component is given by r times theta double dot times sine phi, plus r dot times theta dot times sine phi, plus 2 times r times theta dot times dot phi times cosine phi. Its phi component is equal to r times phi double dot, plus 2 times r dot times phi dot, minus r times theta dot squared times sine phi times cosine phi. Now we can use these results to give the components of the different kinematic quantities in these coordinate systems. Then we can list the coordinate expressions of kinematic quantities in all the three coordinate systems. Here we show a table with the columns for the Cartesian, the cylindrical, and the spherical polar coordinates. In the first row we specify the position vector r, as a function of the time t. For the Cartesian coordinates we have the coordinate functions x, y and z. For cylindrical coordinates the coordinate functions are ρ, phi and z. For spherical polar coordinates the coordinate functions are r, theta and phi. The next row contains the velocity v, as a function of the time t. The velocity components in Cartesian coordinates are just the derivatives of the coordinate functions x, y and z. We also show the square of the length of the velocity vector, which is its scalar product with itself. Then it is just the sum of the squares of the derivatives of the coordinate functions. In cylindrical coordinates, the rho component of the velocity is the derivative of the coordinate function ρ. Its phi component is equal to ρ times the derivative of the azimuthal angle phi. And its c component is simply the derivative of the coordinate z. The square of the length of the velocity is the sum of the square of these components. And it contains squares and quadratic terms of the derivatives of the coordinate functions. In the next column the components of the velocity in spherical polar coordinate system are shown. Its r component is just the derivative of the coordinate function r. Its theta component is r times sine phi times the derivative of the vertical angle theta. And its phi component is r times the derivative of the azimuthal angle phi. Again, the square of the length of the velocity is the sum of the square of these components, with squares and quadratic terms of the derivatives of the coordinates. In the third line of the table, we can see the acceleration a as a function of time. The components of the acceleration in Cartesian coordinate system are the second-order derivatives of the coordinates x, y and z. The square of the length of the acceleration is the sum of the square of these components. In the next column we can see the acceleration written in cylindrical coordinates. Its ρ component is the second-order derivative of ρ, minus ρ times the square of the derivative of the azimuthal angle phi. The phi component of the acceleration is equal to ρ times the second-order derivative of phi, plus 2 times the derivative of ρ times the derivative of phi. And its c component is just the second-order derivative of the coordinate z. As in the cases of the previous coordinates, the square of the length of the velocity is the sum of the square of these components. The components of the acceleration in spherical polar coordinates are even more complicated, but they have common patterns. Each component of the acceleration contains the second-order derivative of the corresponding coordinate, and the squares or quadratic terms of the first-order derivatives of the other two coordinates. The square of the length of the acceleration is the sum of the square of these components, which is a very lengthy expression, thus we do not show it. Now we see that the kinematic quantities have the simplest forms in the Cartesian coordinate system, and their components have the most complicated expressions in spherical polar coordinates. However, sometimes the motion of a body exhibits some symmetry, that is, the body moves along some regular curve, for example along a circle in circular motion. In such cases, we can utilize the cylindrical or spherical polar coordinate system, since the components of the kinematic quantities reduce in a great extent. Then the description of motion becomes simple in any of these coordinate systems adapted to the symmetry of the motion.